To get straight to the point, let's talk about what makes a distributed system. I imagine some of you already know about distributed systems. It's a macro category in informatics that fundamentally can be identified as a system of coordinated computers that work together, and on this basis we can distinguish various types of distributed systems for different applications which seek to solve this type of problem. So fundamentally, I've got a central server and I have a series of clients that rely on a central system. I can increase the RAM, I can increase the hard disk, but I arrive at a certain point in a bottleneck due to physical conditions of the hardware. And so I need to distribute this type of system. Probably you all know of the concept of load balancing. I build another computer that is probably the twin of the first one, and then I put a layer in front. This is just yet another computer that does the balancing of a series of connections. Completely algorithmically, it decides which operation to send to which computer. Behind all this is a system of synchronization that is clearly based on the load balance, and that is not in the least concerned about how you've got to synchronize the data at the back of this. So if it was, say, a classic website with a lot of load, probably the static content will be copied arbitrarily in the folders of the various computers. If they make use of a database, the choice might be to put a central database behind the two computers, or to have two databases and something that synchronizes between them. This is the classic distributed system as it is known these days in IT systems. But this is not the only motive. For example, a distributed system can be used to distribute the connectivity between various countries. I can imagine that if this is the world, which I have to draw flat, and this is Australia, and this Europe, there is a significant latency time. If I decide to put the server in Europe, those in Australia will have a latency of at least 4 or 5 seconds to arrive at the contents. And the same will happen the other way around. So probably putting the node in the middle is not the ideal solution. It will put everyone at a disadvantage. In this case, one creates what is known as the content delivery network. So there are these computers in a load balancing model that are synchronized, so that a client in this place will probably be redirected towards the nearest network. And then inside, there will be the exchanges that allow the use of all the content without the latency time. Another scenario might be that of having distributed resources. That is, I could have an application, Netflix for example. I can have an environment in which there are video contents, and this is distributed for the motives we talked about earlier. An environment with database resources of subtitles and all the information in another environment in which I need to put the bidding plans, credit card payments, then probably there may be a social network. This is a microservice architecture in which the systems collaborate between themselves to function, and this model is nevertheless a distributed system. And in this case, what is being distributed? The logic is distributed, not the same contents. Whilst in other cases, presumably the data is twinned on two different computers, which is not only unnecessary but counterproductive, and we try to isolate these things. Now, as long as we are just drawing on a screen, it's all neat and tidy. But in reality, there are complexities of a mathematical nature. In keeping these systems aligned, especially in the cases mentioned of the failure, because clearly, depending on the scenarios, if we don't return to the part of load balancing, fundamentally, if one of the two fails, I could have strategies so that if it breaks down, my load balancer stops sending it requests. It will increase the load on the first one but a technician can intervene to repair it. In the second case of the CDN, the same thing. If one breaks, one of the others takes over. In the third case, if one breaks down, the system stops working. So, when you start to design a distributed system, it is necessary to keep in your mind the motive for distributing and the techniques for designing the management of failures depend to a large extent on the modality in which it is designed. That being said, all these distributed systems, I haven't mentioned the blockchain, but we'll get there. All these distributed systems have something in common. Generally, they do not have a single point in which decisions are made, but due to their distributed nature, they have rules that depend a lot on the system in general. Okay, another important thing is the management of the failures. All the things that we saw before function extraordinarily on paper. Today, we're no longer aware of any problems that might have been in the past with the DCP protocols. There are packages for sale and other solutions. So for many things, the tech industry has reached an advanced level where you don't have to worry about whether a packet will arrive or if a message is consistent and all that. In reality, the big companies, and we saw not long ago with Facebook that went off for a while. So if any of you has a site that goes off for half an hour, at worst you call someone. Over there, millions got moving for a small intervention. These things, at a certain level, begin to be no longer negligible, even because amongst all the systems that get turned off, the security system goes off. So the problem is not that you can't see the photos in Twitter or whatever. The problem is that the failure forms part of what in technical terms is known as the CAP Theorem. Who has ever heard of the CAP Theorem? The CAP Theorem. The theory of the CAP fundamentally says that all distributed systems are based upon three major characteristics: consistency, availability, and partitioning. So, a distributed system we can see equally as a database or a series of databases that are synchronized, and these databases probably must be consistent. What does consistent mean? It means that if I make a request at any moment at node 1, node 2 or node 3, I must get the same reply. This is something that does not go without saying, because if I insert data in node 1, it must propagate it to node 2 and node 3. So, ensuring the consistency of the data means that, and some databases are structured to do this, until all three databases are aligned, the data is not available. So, imagine the addition of a new user. I make an insertion in a database, and then after an instant, I go to do the get from the databases. Some databases will tell you that the data does not exist. You say, come on, I made an insertion. I have the ID of the user. I go and do the get, and you tell me the data doesn't exist? All this because to ensure consistency, that data is not available until it is certain that all other databases have taken it on board. What's the reason? Anomalies could happen. It could be that around these three synchronized databases, there are applications, and maybe the load balancer randomly decides to draw from database 1, 2 or 3 for performance reasons. I go to insert a user. The application at a conceptual level inserts the user, takes the user and changes their name. Maybe the insertion takes place immediately on one database. The update takes place on another. the other databases are not synchronized, and a disaster happens. So in guaranteeing the consistency in distributed systems, sometimes technological choices are made to the disadvantage of some concepts. The other is the availability of information. Availability means that I can be sure that if I put data in point 1, I have no interest in looking for it elsewhere because it is my closest point and it will calmly propagate the data. But I, knowing that I've entered a user into the Italian system, have no need to go and look for it in Australia. I'm going to look in the Italian database. Then if Australia synchronizes for its own reasons, it will do so over time. This means availability, i.e. the fact that I have the possibility to have availability of the data in any circumstances by organizing myself in advance, knowing where I put it before and to take it from there, so I don't have to wait for the consistency. This is clearly the partitioning, the fact of being able to partition the data within a network. It can be demonstrated mathematically that all three elements cannot coexist at the same time. This is why they are recognized and why the CAP theorem exists, because mathematical phenomena come into play and some physical aspects, such as the speed of light, affect the latency of the networks, for which it can be proved, not by me, but by someone who did it in place of me, that these three elements together cannot coexist. So it doesn't mean you can't make distributed systems. It means that knowing the CAP theorem when designing a distributed system, you have to choose exactly how to approach it. And on this point, I will draw a very simple diagram. Imagine Twitter. I have my databases. We'll put them in 3 different geographical locations around the world. I tell you, this is our CAP. Let's try to understand what choices Twitter has made in designing its architecture. If I'm in Italy, and I insert a tweet in Italy, and this tweet in an instant is on my Italian site, and in 20 seconds is available throughout the world on my profile, even America, for me, it's a problem, or is it tolerable? No harm will come to anyone. So what have Twitter, Facebook, and the rest chosen to do? They have chosen to sacrifice consistency. All the databases are perfectly aligned to give precisely absolute priority to availability. This means that if I make a tweet in Italy, that tweet is immediately available in Italy, but not in other countries. Little by little, it will arrive in the other countries. If they hadn't made this choice, my message wouldn't have appeared before it had appeared in all the servers. This would have created a problem of user experience, because I tweet, then I don't find my tweet, so I panic, ask what's happening, I repeat the tweet, then delete, creating useless traffic to the detriment of the system. So, you voluntarily choose to give up consistency, to give priority to partitioning and availability, and that goes for the social network. Let's take another example. Let's look at a bank, a distributed bank. So there is a copy of my current account in Italy, in London, or rather in Sydney and in San Francisco. I make a payment and my balance goes from 10,000 euros to 9,000 euros. I submit my payment to the Italian database, and then it has to synchronize all the others. You think it's a problem if they don't synchronize immediately? what can happen? So, the banking world has made its choice, CP. That is, to guarantee the consistency, it has chosen CP and has sacrificed availability. This does not mean that the balance is not available, but it means that if I make a bank transfer, it will not be executed until all the systems aligned. So, I have paradoxically lost availability, though the banks have some tricks up their sleeves. But if I go to my bank, I don't see my movement immediately. So sometimes I think that the bank draft has not even set off. Have you ever made a draft and then you don't see it in the list of movements? This happens because they have decided to accept availability as a problem for the benefit of consistency and partitioning. You may well have your own ideas, but if so, you could be competitors for the Nobel Prize. But in reality, the people who have looked at this problem around the world, they realized that there's just no way to ensure to everyone that they can have all three things at the same time. It's just not possible to have everything you want in this world. You realize that even the speed of propagation of the data damages the system. So, in this case, we have a system CP. C for consistency and P for partitioning, which are the priorities of this system. So, the system CP is the banking system, where the availability will eventually arrive. We say eventually consistent, eventually available, which means we haven't neglected this third factor, but it will arrive at some time in the future. It certainly will arrive, but only eventually. So, we can have a quick look at a CA system. A CA system is one in which we have renounced partitioning. How do you set about renouncing the partitioning? So, this system can apply to banks. Banks use a system of eventually partitioned. Let's think about bank gyro payments. Bank gyro payments operate with a central system. So, distribution, excuse me, I forgot to say, when we're talking about partitioning, we're talking about network partitioning. You can use it in other terms, so fiber optics, but in this case, we're saying the source is remote in some way. It's not in the same computer. It's not managed by the same processor. To be clear, when we're talking about partitioning, we're not talking about partitioning of the disk. We're talking about partitioning of resources. Two computers next to each other, connected together by the network, where the management of the resources is managed by somebody else. The CA system, the system is eventually partitioned. I can consider, for example, in the IBAN code, which identifies the bank and the current account, to move that account, even if all the bank is synchronized, I must ask explicitly that resource. Let's say there are three distributed systems. Luca's account is managed by resource 1, computer 1. To make a bank draft, I must go through computer 1. That's where Luca is. Then afterwards it goes into the system. What's the difference with the previous system? Before, I could make a draft anywhere, and then afterwards the others would get themselves sorted. In this case, I must make the draft on a specific resource. If I try and do it on this resource, he'll say no. The draft, it'll do it, and then tells the others that it's been done. What is the guarantee? The guarantee, the consistency is no longer there. I can't go and check in San Francisco, but it doesn't matter. Because when I want to use that information, I have to go through a system. Is it centralized? No, it's distributed. But it's centralized in the logic of the application. So if paradoxically R1 breaks down, it doesn't mean I can't have access to my money, because my money over time will be synchronized on the others. But I lose the opportunity to do these things, but after a while the technician puts it all right. So I'm being on a quick route through PCA. Let's see where the blockchain fits into all this. We can't talk about blockchain unless we talk about how blockchain was born. So everyone has their fantasies. It could be Satoshi Nakamoto who invented this project. I'll tell you my theory. I've seen that in some contexts it's difficult to find a real truth, but there's some good stories to tell. Somebody tells stories, some people tell their stories. You can think about it yourselves. Blockchain does not start in the context of Bitcoin. It probably was born in areas known to you. You don't have to be a fanatic of e-mule. You've seen it, you'll know about it. I had a friend who had e-mule at home, okay? E-mules worked really well, and still does. What happens if one of you wanted to open a site of file sharing, a pirate site? Let's call it allshare.eu. Everybody can get access to it. It's simple. A dot box. After a few days, the telecommunications police get involved. Let's see what they do. Let's see how a website is made. There's network connection. There's a hard disk with maybe a file of pirated material. Here's a web interface. This server is in a network, an internal network. Let's call it a 192.168.0xx. And there's a gateway with a van. And here's the internet. The van has the rule that if a request arrives at gateway 80, it sends it to the server. So nothing else has incoming traffic. And here's a DNS with an IP public, a public IP that maybe is 178, 12, 15, 2, 20, okay? And here, there's the computer of somebody at home, who's navigating to arrive at that IP address. It's a public IP address that corresponds to this. And so I end up inside the system, and I can get at my pirated material. What are the weak points of this system? How can the police close this down? How can they kill such a system? The IP address is maybe it's Vodafone. if you were the police, you're playing cops and robbers, we've got to turn off this system. You have any tool you like. How would you do this? How would you close it down? You could do it by looking through the connectivity. Vodafone, who did you give this to? Close this down. And Vodafone closes it down. This is the most serious way of doing it. A less serious way of doing it, you go to the DNS. Lots of people don't navigate for IP addresses, they use URLs. So for the site allshare.io, there'll be a DNS record of A-type DNS record, which says that this IP address takes you to allshare.io. This is a naive way of doing it, because if you know the IP address, you can go straight there, bypassing the URL. Okay, so there are moments where it is possible to impede the distribution of pirated material. It's not easy, but... And if you want to design a system that could survive such an attack, what do hackers do? The hackers have begun to put copies of this computer in various places. So, if one address is blocked, they use another one, then another one, and they survive. But there's always someone who has to do maintenance. If it's broken down, I move it. It's broken, I move it. Nutella and others have found other ways of doing this. They've found a way of doing automatic maintenance. The CAD protocol, any of you know this protocol? This is something you don't study at school. We technicians learned about this not from official texts, but from the passion to go looking for it with a passion. And we want to see how we can use it to our advantage, not to solve a problem. The system, the CAD system, is at the end of the day simple. It's a self-adjusting system. A self-adjusting system has a central server. Let's call it allshare.io, which does not contain the pirated files. It contains a database with a list of the IPs where the pirated material is. This is not illegally. It's simply a list of IPs. If within this list there's something illegal, it's like going to the post office with a telephone book and saying that in the telephone book there's a mafia killer, Provenzano, and you can't say the whole telephone book is illegal. So I have my central server with all these IP addresses, and everyone who looks at this list can see the lists of IPs and begins to collaborate. If I'm the first node with my files, my pirated files, I connect to a version node. Who are my brothers? The debate says, here's 1 and here's 2. I go to 1. Give me the files. He copies in and he's cloned the first pirated node. So he's got a second copy. A third arrives. He makes a push on the available IP address. So it repairs itself, but it has a problem. Here's the problem. If we go back to cops and robbers, the way of blocking this system is to demolish that bit. If I demolish this, I've removed the coordination of all the others, and so the system cannot collaborate. CAD doesn't work like this. Many do it like this, but CAD doesn't. CAD has made a step forward. CAD says, let's look at the central system. We shouldn't have one. We have to make a system that works on a legionary basis. No central system, no central point which is functional for the whole system. But this is what the specification of CAD. No central points. Okay, eliminate the central points, what happens? How can we make people coordinate without a central computer? Okay, there's another computer, another part of the world. A good way, if I know this one and he knows me, if we had each other's IP addresses, we've exchanged them, we can start collaborating without a central layer. But we have an RCD, which becomes a central system. You can give it a range of addresses, but it's copying previous ones. So how can we do this without anybody knowing where we are? No one should be involved in the negotiation. This is done with a broadcast technique. When you send a packet on the web as a ping, you just send a number, which is a broadcast address. If I set it to 10, it arrives at 10. We won't go to how it works, but it's more of a conceptual ring than a physical ring, that it goes to everybody. If I turn on a chat, I see all the traffic, but it's a mess of data in which, if I want to send a message from 1 to 3, I don't do it like this. I send a message that goes to destination 3, I send it to 1. He says it's not for him, so it goes to 3. 255 is a trick. Could be another number. So 3 is programmed to take everything that goes to 3 and to 255. And this rule works on all the kind of onion rings. Okay, the dark web works in this way, the Chipola principle, the onion principle. Number 1 sends a message saying, I exist. He says it in a particular way. So if I intercept it, I block it, and I block you. But he sends it encryptedly. So it has no meaning what I send, but his other brother knows how to decode this message because it belongs to that network. So within a broadcast system, and he says to everybody that he exists. I can hear that the number 2 computer is a fratello of number 1. So it has the same software, so he understands what it is. He understands to code and how to decode. So when I get a message of this nature, I can understand it, I know how to interpret it. And it says, I'm 1, and you can contact me here. Only 2 understands this. And Tan sends messages all the time. I exist, I exist. And so when 3 turns up, 3 gets information from 2 and from 1. This is the conceptual level. At the physical level, you go further. When 2 tells you it exists, he says, I already know this. So we get a propagation of relationships without a central system. This is the Academia protocol. It's the protocol that we use at the center of our system, which permits the node to do self-discovery without going through the central node. We've seen the importance of a central system and what's the weakness of a central system. How would you design a system like this? Cops and robbers. Nobody's managed so far. If I turn one off, this one here, the system will continue to work because another model will appear, it will self-synchronize, and when the speed at which the nodes appear faster than they get turned off, you've created the immortality of the system fundamentally. So now the Nutella system, the CAD system, are those that permit file sharing, like T.R.I.N.C.I is a hybrid of this. It is a central system where it uses a different system for dispersion of the data. Just for completion, T.R.I.N.C.I is more vulnerable relative to others, but it works with a lot of skill. So it doesn't use certain types of servers. If I on server 1, I've got a film of avatar. I possess the copyright. I mean, I'm being illegal. So the authorities just have the right to turn me off. If I only have half of avatar, I only have half a film, which may still be protected by copyright. But if avatar is just a sequence of zeros and ones, and I only have the multiples of 4, I haven't got avatar. I've got a series of zeros and ones, which would not make avatar. They're just 0 ones. They don't contain fragments. This allows me to have a server which has the information, part of the information, which makes up avatar, but singularly, it's not together. Somewhere else that has complementary information. So with 3 systems, the file is complete. But where is it complete? Singularly, it's not complete. But if I do repicking from here, of the data, I can recompose the film of avatar. This is a decentralized system where it is easier to manage legally. Because I haven't maximized the hiding of the data. Because who's compromised here? It's the user. It's whoever downloads the film avatar. It's whoever's downloaded the film is in the legal position. The others are not acting illegally. It's strange, it's anomalous, but distributed systems do this. So why do we talk about illegal things? Because there is no system is more resilient than a legal system. So what terrorists use are what function. Maybe heads of state use these systems because they've seen that in hostile contexts, they're resistant. And Affidaty has made the same choice. It hasn't decided to invent a new Napster, but to avoid an important problem, that of the blockchain. Okay, we get back to the road of the blockchain. Our road takes us on an important step. You're here in Affidaty, you want to see how this technology works. If you trust this network or you don't trust this network, if you take a software from Affidaty, taken from us, managed by us, with a central server, you choose Amazon maybe. So you don't worry about blockchain, you put a technology. Blockchain, database, doesn't matter. You're paying Affidaty to have this technology. You do your business, you make your website, you make your apps, you do whatever you want. Affidaty one day forgets to pay the bill to Amazon. No more money, I'm not paying Amazon. Amazon closed down the service. But you've based a system. You've based a system on this. So if this closes, what happens to your system? This is the central system that you must defend yourself from. On the one hand, you had to defend yourself from the police, who would attack your central server. There was a good motive for closing you down. This Affidaty could close down just for business reasons. So it's not a good idea to use technology provided by one business. Why am I showing you this? I've raised this point because it's important to realize that blockchain can be important for the survival of some projects, some softwares, because we can begin to remove points of weakness in the development of what could be the core of a business. It's easy. On Oracle, you buy software and you install it. It's fine for everybody. But that's Oracle. It's big. And it's difficult to imagine that it fails or that Google fails. But Facebook has changed its name. In front of a few people's eyes, suddenly we saw Mega. Imagine what happens if you do business on Facebook, and at a certain point you discover it's not like that anymore. What happens? Important things happen for the business. Of those who choose a certain technology and certain applications, to know that what you trusted all the time isn't there because someone has decided for you, it's like the police closing down a site. It's the same thing. That's why we've created a decentralized system, not for motives of legality, but to remove Affidaty from the centralized governance. So, if Affidaty didn't pay Amazon, probably the Affidaty system went down, but not its technological ecosystem.